Alright, our method skeleton for the TP motor class is now in place, and now we're going to add in our functionality for the snap-align with camera method as well as the process motion method.
Right. We're going to start with snap-align character with camera because it's the simpler of the two. Now if you remember back to our theory video, we said it's going to look and see if we're moving or not, and if we are moving, it's going to align our character with the direction of the camera. So to do that, we're just going to do an if and say if move vector dot x does not equal 0, or our move vector dot z does not equal 0. So basically, if we're moving in either x or z direction, we're moving, go ahead and snap our character. If not, don't do anything.
Okay.
Now to snap our character, we're going to take this character's transform, and we're going to find his rotation, and we're going to set it to a new quaternion. So we're going to take a quaternion, and we're going to build this from an Euler, and the Euler takes in a vector 3. Or I can split it up into x, y, and z, and I'm going to use that overload. So to get our x, we're going to pull our transform again. We're going to take our Euler angles, which is our rotation, but in Eulers instead of quaternion.
Right.
So we're going to take our x from our character's controller.
Which really just means we're not touching x. We're leaving it set to whatever it happens to be right now.
Exactly. But we're going to take our camera, we're going to take camera's main camera property, which is pointing to our main camera. We're going to take our main camera's transform. We're going to get its Euler angles, but we're going to take its y rotation.
So we'll take the y rotation of the camera and use that to replace the rotation of our character, which is consistent with the description we had of the behavior, where we're going to rotate the camera to match wherever the camera's... Well, I'm sorry, rotate the character to match wherever the camera's facing.
Right. And with the z-axis, we're again going to go back and take our character's z-axis rotation.
Right, because we don't need to change the z-axis.
Yep.
We're going to be rolling the camera.
So that is all we need for snap-align with camera. It's as simple as that. Now process motion isn't much more complicated. There's just more steps.
Okay.
So if you remember, again, back to the theory, we do this in 5 steps. First we transform our, it helps if I can spell transform right. We transform our move vector into world space relative to our character's rotation. So that's going to be our first step. Our second step is we're going to normalize our move vector if our magnitude is greater than 0.
Okay.
Once we've done that, we're going to set a new magnitude for our vector based on our move speed. So what we're going to do is
multiply the normal by our move speed. I'm sorry, our more normalized vector.
Right.
So move vector, thank you. Oh well.
What's that?
Oh, I'm just laughing at myself.
After we've done that, our move vector will now be in units per update or units per frame. We need to convert that to be units per second.
Okay.
So to do that, we're going to multiply our, can I spell multiply right?
Well, we've already established you can't.
Yeah.
Twice now.
Multiply. Yeah, you know, I like making up words.
I was going to let it go, but then you brought it up. So.
Well, I looked at it, it's like, that can't be right. So.
Right. So we'll multiply the new move vector
by delta time.
And that's going to change this over to a value per second instead of a value per frame.
Once we've finished all that, our calculations are actually done. We now have to move our character in world space based off of this vector that we've done all the math calculations to.
Okay.
So we will move the character in world space. Now, the functionality is quite simple. It's only 5 lines of code. So what we're going to do is take our move vector, and we're going to take our transform's built-in method called transform direction, and we're going to pass move vector into it.
Okay.
So that will handle the transformation of our vector. For normalizing, we just say if move vector dot magnitude is greater than 1, assign move vector to be equal to what is returned from vector 3, normalize by passing in the move vector. So we're passing in the move vector, it gets normalized, and then it reassigns move vector to be the output of the normalize method.
Okay. Nice.
Now we take the move vector, we times it by our move speed, or multiply it by move speed. So that sets our magnitude for our vector. Now to convert it into delta time, we will take our move vector and we will times it by the built-in property of the time class called delta time. That will convert us from units per update to units per second.
Now, what is delta time exactly?
Delta time is the time difference between the last update and this update.
Okay, multiplying by that, we can speed up or slow down to match seconds.
Right.
Technically slow down. I mean, it should be slowing down unless you have
a real slow computer.
Yeah, unless you have a really slow computer.
Now, the last part is actually moving the character, and this goes back to why we created that static field in TP controller that they'll hold the reference to the character controller.
Right, because now we get to use that.
Yep, so I can call TP controller dot character controller and tell it to use its built-in method called move, and I just give it our move vector. And that is all we need to do to implement the motion inside of the motor. We still can't run this because we're not sending the information from the TP controller to the TP motor yet.
No, as you recall, in TP controller, all we've done at this point is we've established our skeleton. We haven't actually added all of our functionality in yet.
Right. So in the next video, we're going to go add that functionality.
Sounds good. Let's go ahead and jump into it. Thanks for watching.